So today I'm going to talk a little bit about what are called axiomatic systems, or axioms, and how we prove things using axioms. An axiom, first of all, I want to define what an axiom is and then talk about what an axiomatic system is from there. The key thing to know, though, or the key thing to take away, is that axiomatic systems are a way of putting together a few things that we're going to assume to be true without giving them proof, together with undefined terms. And then we use those axioms, those statements, along with those terms to either define other terms or to prove theorems and propositions and so on. So I'm going to start off by defining what an axiom is. And an axiom is simply any statement which we assume to be true without giving it a proof. So you might think about some examples in your own life. An axiom that you probably believe is that the sun is going to rise tomorrow. Now there's strong evidence that the sun is going to rise tomorrow. For example, it's risen every day in the past, so why should tomorrow be any different? But a lot of evidence isn't necessarily a proof, and so we can't prove that the sun is going to rise tomorrow. We can give a lot of scientific evidence and predictions that it's going to, but there's no fundamental proof that that's a true statement. So you might try and think, what are some other axioms that you believe, either about life or about math? What are some things that you believe despite not having some sort of rigorous proof of those things? And mathematics is a lot like philosophy in this, where it starts by just proposing a few simple axioms and then building off of those axioms and those undefined terms to give some complicated results that follow directly from those axioms using only logic. And so I just mentioned another term, which is undefined terms. And an undefined term is really just any term which is undefined. It's anything that we use in talking, use in speaking, and use in math, where we don't necessarily give it a clear meaning. And so you might, a good example of some undefined terms would be, for example, a point, a line, and a plane. In standard Euclidean geometry, these things are all undefined. You can try and give a definition of a point. You might say, well, it's a zero-dimensional thing that lies in space somewhere. But then you're running into the question of, well, what does it mean? What does it mean to be in space? What does dimension mean? And you come across a whole bunch of other terms that you've thrown in there without giving them a proper definition. And so eventually you're going to hit rock bottom. You try and define all of these terms until you either have to go back and circle around to use a term you've already used, in which case your definition becomes recursive and is not a good definition, or you just keep going and spinning your wheels and never hit the bottom, in which case you're not really providing a definition, you're just providing me with a list of more undefined terms. And so in standard Euclidean geometry, these three terms are all undefined. Okay, so once we're armed with the idea of axioms and undefined terms, we can put them together to come up with what's called an axiomatic system, which is just simply going to be any collection of undefined terms and axioms. So try and give it a moment's thought. I mentioned the example of geometry already. You might think, okay, what are some of the axioms of geometry? I've already given you three of the undefined terms, so point, a line, and a plane. And you might start thinking about some either definitions that you remember from geometry, or different propositions that you believe from geometry. For example, do you believe that if I've got a point and I've got a line here, how many lines are there that run through this point and that are perpendicular to this line here? Well, you would probably say there's only one, that one. And if you're thinking about standard Euclidean geometry, you would be right, because that's how we define that. But there are other forms of geometry where we get rid of some of the different axioms, where we throw them away. And that statement that there's a unique line crossing through that point perpendicular to the original one, where that might not necessarily be true. And so even though we've got some intuition about what these three terms mean, when we start introducing different axioms, our definitions or our intuition behind what these terms means can kind of go out the window. So you have to be really careful when you're playing around with axiomatic systems to use only the terms that you're given along with the axioms and any definitions of terms, of other terms, to prove some sort of statement. You also are probably familiar, even if you don't really realize it, with some of the axioms of the real numbers. So here I'm just gonna list out a few of those. One of those for example, is that addition is commutative, which means that y plus x equals x plus y, or x plus y equals y plus x for any real numbers. You probably believe that without any sort of proof. Another thing that we assume is that addition is associative. So if I want to, I can just shift these parentheses around, give me something like this. What are some other things that you can think of? Well, the real numbers also satisfy. They have to play nice with addition and multiplication together. So you might have to figure out a way of figuring out how does multiplication turn into something that works with addition. And while we have this axiom, this thing that we don't really prove, we just say, let's pretend it's true. That gives us this. And so you have to be careful when you're dealing with axiomatic systems that you're aware of what the axioms you have are, so that you're not disobeying any laws just because your intuition tells you that it's true. So, for example, you probably believe that 1 is a number that's different than 0. But in some axiomatic systems, that might not be the case. And that's actually something that you would have to prove or disprove. But kind of the beauty of math and part of the creativity is that even though we've got all of these axioms that we assume at some point or another, we can throw some of them away and challenge some of them to see, well, what would happen if we didn't assume some of these things? What would happen if we didn't assume that addition was commutative? Or what if this isn't how multiplication and addition act together? What happens at that point? What are some of the things that we can prove then? And so that's what axiomatic systems give us, is a way of formalizing what sorts of rules we can mess around with. But then it also lets us figure out, well, what if we didn't play by those rules anymore? But once you've got an axiomatic system, if you're following that system, you've got to be careful to follow those rules. So here we're going to look at an example that I've modified from the textbook that I'm pulling some examples from. Here's an axiomatic system where I've got a few undefined terms. So I'm going to try and color code them. One of these is a verb, that's to grok, and the other two are nouns. So we've got dak, snood, and to grok. And then we've got these 4 axioms. The first one says that every DAC groks exactly 4 snoods. Okay, so we've got a DAC and it's grokking exactly 4 snoods. Okay, we're also told that every snood is grokked by exactly 2 DACs. Okay, and then the third axiom is that if x and y are distinct DACs, I wanted to change that. Each grokking okay, so if we've got 2 distinct DACs, each grokking the snood Q, then there are no other snoods grokked by both x and y. And the last axiom says that there's at least one snood. And the thing that I really want you to take away from this is that you should not have any experience with the words DAC, snood, and grok. They should be completely nonsense words. But part of what this is getting at is that even though these are undefined terms, our axioms give them meaning. And the context of these axioms tell us the rules by which we can mess around with DAC, snood, and grok. So actually just using this axiomatic system, we can come up with a theorem that says that if Q and R are distinct snoods, both of which are DAC'd by So we can come up with a theorem that says if Q and R are distinct snoods, both of which are grokked by DACs x and y, then x and y actually have to be the same. So here's that written out at the bottom. So this is the theorem that we're going to try and prove. So we've got 2 different snoods, Q and R, and each of them are grokked by the DAC x and by the DAC y. And we're supposed to show that x equals y. And the only tools that we have are our axioms up here. So how do we use these axioms to prove this theorem? Well, I'm going to go ahead and use a proof by contradiction. And to do that, I'm going to suppose that that Q and R are distinct snoods. And that X and Y are distinct DACs. Are distinct DACs which grok both Q and R. So this is my the thing that I am supposing. So this is what I'm given. And maybe I should say here, and suppose to the contrary. So I'm going to suppose that Q and R are distinct snoods. So we've got a snood here and a snood there. And that X and Y are distinct DACs. And each of them grok both Q and R. And using only my axioms, I'm going to show that that this is a contradiction. And actually it follows almost immediately by looking at axiom 3. And why is that? Well, okay, so I've got X and Y that are distinct DACs. So axiom 3 is going to tell me if X and Y are distinct DACs, okay, X and Y are distinct DACs, each grokking the snood Q. Okay, so X and Y are distinct DACs which grok both Q and R. so in particular they grok q, then there are no other snoods grokked by both x and y. Well, here x and y are distinct DACs, they're distinct DACs. They grok q, but they also grok r. And so what axiom 3 is telling us is that, well, their x and y are both grokking q, so we would have to have q and r be the same snood. Otherwise, axiom 3 would have been false. But we already are supposing that q and r are not the same. We're supposing that q and r are actually distinct snoods. And since these axioms are what we're supposing to be true no matter what, that means that I've got a contradiction. Axiom 3 is telling us that q and r actually have to be the same thing. But by what we're supposing, q and r are not the same. And so that leads us to a contradiction, which means that we have actually finished the proof of this claim, of this theorem. Okay? So if you're unfamiliar with proof by contradiction, I'd suggest that you take another look, pause the video, see if you can figure out why we have this contradiction, and see if you understand how this axiomatic system gave us that contradiction. Okay, so here's a model that helps us understand the DAC-SNOOD axiomatic system a little bit better. The key thing to know, though, is that we, even though this is a way to represent the model of the DAC-SNOOD axiomatic system, it's not necessarily the only way. And so this picture here doesn't necessarily give you a proof. It just helps you understand maybe another way of seeing what's going on. So if we were to say that a DAC is a square, and that a snood is a vertex or a corner of that square, and that to grok means to touch or have, then we could rephrase this theorem to say if q and r are distinct snoods, so if q and r are distinct vertices, both of which are grokked, both of which are touched or had by the squares x and y, then x and y actually have to be the same square, which should make sense. If you've got two different vertices, and you've got two squares that share both of those vertices, then looking at this as our image, well, the only way that can happen is if you've got the same square touching both of those vertices, which means that it's the same square. So maybe to make that a little bit more clear, this picture is the image that we're using as a model for understanding the DAC-SNOOD axiomatic system. And you can check that all of the axioms are satisfied by this picture. And again, you should be careful that just because we've got a model here, that doesn't mean that this model provides us with a proof. This model just helps us understand the proof a little bit better, perhaps. So the exercise that you are supposed to do now is explain using the DAC-SNOOD axiomatic system up here, which I'm going to erase the color coding for. Using this system, your job is to explain why there must be at least 7 distinct snoods. And you should make use of this axiom, and you're probably going to want to make use of this axiom as well, and probably the second axiom. Okay, and again, this one here should say grok. So take a little bit of time, pause the video. I'm going to end the video here. Try and figure out why it is that using the DAX-snood axiomatic system, try and explain why there have to be at least 7 distinct snoods.